the velocity problem. Velocity is a type of rate of change, as we discussed in the previous slide. Units of it are miles per hour, kilometers per hour, feet per second, meters per second, and so on and so forth. You have a device in your car that you can actually find the distance you traveled. So the average velocity, if you know how many hours you spent traveling that distance, then you can find the average velocity basically. So that's one thing. And then you have another device in your car, on your dashboard, that tells you the instantaneous velocity basically at that very moment. So let's start with this question. The question is asking, a ball is thrown upward with a velocity of 40 feet per second. The height in feet t seconds later is given by this rule of this function, y equal to 40t minus 16t squared. Find the average velocity of the ball between times 0 and 2, 1 and 2, 1.5 and 2 over those intervals. And so to find, for example, the first interval, what we do is we plug in 0 and 2 into the distance formula, the height formula. And so, for example, y at 0 is going to be 40 times 0 minus 16 times 0 squared, and that's 0. And then y at 2 is going to be 40 times 2 minus 16 times 2 to power 2, which is going to be 80 minus 64, and 80 minus 64, which is 16. And then to find the average velocity in over the interval 1, we're going to go 16 minus 0 divided by 2 minus 0, which is 8. Okay. So that's the first average velocity that we find. So we found the average velocity over the intervals 0 and 2. That was 8. What does that mean for the graph? So this is the point 0 and the y value 0. If I plug in, that's the point. So this one is 0 and 0. That one is 2 and 16. That's what we found. And so if you connect the two with a secant line, then the basically the average the slope of the secant line is going to be 8, is the average velocity that we found. And so that's the slope of the secant line. Now, what about the second and the third one? The same process applies. For the second interval, you again plug in 2 into the y, and this time you will get 16. And you plug in 1 into the y, and you get 40 minus 16, which is 24. And then 24 minus 16 over basically this is the slope of the secant line that is corresponding to average rate of change over interval 1 and 2, and you end up with a -8. So y at 2 is 16, y at 1 is 24, and 16 minus 24 divided by 2 minus 1 will give you -8, which is slope of the secant line. So the last but not the least is the slope of the secant line for the interval 1.5 and 2. So interval, that's x value 1.5, x value 2, and you draw the secant line in there. To find the y value, you have to plug it back in and see what and the slope of to find the slope of the secant line. You also have to plug it back in to calculate the slope of the secant line. And so what you end up with is y at 1.5, which is going to be equal to 40 times 1.5 minus 16 times 1.5 to power 2. And what you get in here, then you will have also you have to calculate y at 2, which we're familiar with. We already did this, and this is going to be 16. And if you calculate that one, you get 24. So you subtract 16 minus 24 divided by 2 minus 1.5, and then you arrive at -16. So we discuss all these slopes of the secant line for this graph, and every time if you look at this, you know the endpoints is always 2 and 16. We started at with an interval, really bigger interval, and it was 8, and then we had another smaller interval, -8, and then we had -16. If we make this interval smaller and smaller, this slope is going to get closer and closer to the slope of the tangent line. What I want you to notice is that when you're far away, though, it doesn't look anything close to the slope of the tangent line. The slope of the secant line does not. But as you get closer and closer, it looks like we're getting closer and closer to slope of the secant line, basically. Now, the tangent line problem. Given a point P on a function f, how do we find the tangent line of f at P? So let's go over here to the link. So here, when let's say we're looking at the secant lines between points A and B, and then as B gets closer and closer to A again, the secant line becomes tangent line. That's a discussion that we had, and this is true for any point. I can move A over here, and again, and as these get closer and closer, there's a limit of the tangent line of secant line becomes tangent line, and so that limit concept comes back in here, and this can happen from either side of A when you're drawing the secant line with points that are getting closer and secant lines that with points that are getting closer and closer to the point that you basically looking for to find the tangent line at. Then those slopes get closer and closer to the value of the tangent line. Is this always true? We're going to discuss all the functions that this is true for, and so the definition basically is that if that limit exists, then that limit is going to be equal to the slope of the tangent line. So the tangent line to function y equal to f of x at a point P is a secant line through the point the point P and a point infinitely close to P on the curve, basically. If it exists, it's basically a limit of the however we define the limit for it is what we achieve by making secant lines in a smaller and smaller intervals, and to end up with a tangent line, basically. Now, tangent slope. There are two ways of defining the slope of the tangent line if it's defined. The first one is, so we're looking for secant lines between points A and B, points with x values A and B, and therefore points A and f of A, B and f of B. So one way is to find the slope of the secant line that way, and that is limit as B approaches A. We saw that in the link that point B was approaching point A, f of B minus f of A over B minus A. So that's the basically the average rate of change. It's the limit of the average rate of change. Okay, so that's one way of explaining the slope of the tangent line. And the other way of doing that is that, let's say not B, but let's say a point close to A, right? Instead of that notation, we use this notation. And so anywhere you see B in the fraction, we replace B by A plus H. And that means that for H that is very small, A plus H is going to be getting closer, and when H gets smaller and smaller, A plus H gets closer and closer to A. And H can be positive or negative, as we saw in the link. It can approach from either side. And so here, instead of B approaching A, because there's no B in here, we know that we want A plus H approach A, that is H approach 0, basically. So we do another example. In a game of Quidditch at Hogwarts, a ball is thrown upward and the height at certain times have been recorded. And so the times in seconds are 2, 2.5, 2.9, 2.95, 2.995, and 3. And the heights are 20, 31.25, 42.05, 43.51, 44.8501, and 45. And these are in feet. And suppose the relationship between time and height is represented by function h equal to f of t. Now, this from the just height time perspective, I can see that if I keep three fixed, and then the other time values are getting closer and closer to 3. So this gives me an idea about looking at average rate of changes that are basically the slopes of secant lines going through 3 and all these other secant lines that are going through 3 and all these other lines, and see if I can find the limit value for that. So let's make another table. And so we make the table like this, and we go in over intervals. Basically, interval 2 and 3 gives me average velocity 25, and interval 2.5 and 3 gives me 27.5. Interval 2.9 and 3 gives me 29.5. 2.95 and 3 gives me 29.75. And 2995 and 3 gives me average velocity of 29.975. So if I'm just looking at this information, it feels like as the intervals get smaller and smaller and closer to 3, and the value of the average velocity gets closer and closer to 30. But here's the thing, I cannot be 100% sure with that. So one reason that we cannot be sure about that is that we don't have enough information, like we don't have enough points as we get closer, even closer to 3, right? And so what is the value close enough to 3 that we can stop and say, oh, we arrive at the correct answer, basically. And then other ways, we started with a game of Quidditch at Hogwarts. Those balls can, in game of Quidditch, can go anywhere they want to, right? And so what if the ball is just over this path instead of a path that goes through all these points? And so look at this one. If I look at all the secant lines through these points, they look like this. They're ignoring the bouncy part of the motion that the ball is making on its own. And so when you're getting closer and closer, you're not really getting closer and closer to a tangent line at point 3 and 45. So this teaches us that we need to know more about the rule of the function, even though a lot of times if we have some knowledge of the graph, we can use the table to find the slope of the tangent line and slope of the table of average velocity to find the slope of the tangent line, or find the instantaneous velocity. It's not always true that we can, basically. And so we have to have some more information if we're using the table only. And that information can be the graph of the function, or other information that we see in the follow-up sections. As far as looking at the rule of the function, is, for example, for this linear function is f of x equal to mx plus b. As far as looking for a rule of the function, we actually have a function that we know, we have a couple of functions that we know the instantaneous velocity for them. The average rate of change for a linear function is the slope of the line of that is the graph of the linear function. Between any two distinct points, it's the same, right? So the average rate of change does not change for a linear function, and so therefore the instantaneous rate of change at any point is also that slope of that line, basically. And so as we progress throughout the course, in chapter 3, we learn more and more about how to find the average rate of change, instantaneous rate of change of many other elementary functions, basically. I click a